at a researcher at ENSAE Paris and also at Criteo AI Lab. And he's going to talk today about his work on selfish robustness and Equilibria and multiplayer bandits. Thank you, Vianney.
Thanks a lot. So yeah, I'm going to speak about this paper that I wrote with my student Etienne Boursier, a great student. And as you say, we are focusing on multiplayer bandits. So the main motivation for this problem, usual motivation, is when you think about opportunistic spectrum access or connective radio. So in this setting, when you have your mobile phone, you can use several bands, frequency bands, and none of them are as good as the other one. Some of them are going to be very busy because the user of this band is going to use it, so you cannot access this band because someone else is using it. And other bands are sometimes they have a high quality, and sometimes they have a bad quality. So the main, if we are looking at this as a single-player multi-arm bandit problem, the question will boil down to finding the band which has the highest quality the more often. But the question is, in real life, there are certainly many players, agents, using their mobile phone at the same time, and they might interfere. Again, the question is, can we define protocols, algorithm, such that the agent can learn which are the best frequency without interfering with each other, because it will lower the global quality of signals. So that was just the motivation. So just to remind you about stochastic bandits, so just one slide, very simple slide. So let's say that you have in single player multi-arm bandits. Let's say that we have k arms, just for notation. And when the player is going to pull an arm, say arm 1, his reward is going to be a Bernoulli random variable, so either 0 and 1. And the value of this random variable, x1 of t, is going to be a mu1, which is obviously unknown. And the objectives of the player, as usual in Bandit, is to maximize his cumulative reward. So that's the easy scenario, standard scenario of multi-arm Bandit. And then we will have multiplayer Bandit. So in multiplayer Bandit, we have all of those arms that are available. So the k arms are still the k frequency. And we have m players that are playing at the same time. They are choosing frequencies they want to use. If they all use a different frequency, everything is fine. They do get, each one of them get the reward associated to their choice. So here player 1 gets x1 of t, player 2 x2 of t, and player 3 gets s4 of t. They're all doing this independently, everything is fine. The difficulty happens when two of them are choosing the same arm. So for instance, here in this case, player 1 and 2 choose the same arm, and so they collide. And the idea is that when if they were using the same frequency, then they will the packets will be lost. And instead of having a reward which is potentially 0 or potentially 1, if x1 of t would have been 1, they get 0. So if two players choose the same arm at the same time, their reward is 0 instead of being x1 of t. Another question is, as I said before, can we define algorithm such that if each player follows this algorithm, the total reward is as big as it can be? So just to summarize things, we have m player pulling arms at the same time, k arms. I'm going to assume, with a lot of generalities, that they are ordered by decreasing order. So mu1 is the best arm, mu2 is the second best arm, and so on and so forth. And if the regret in social welfare is the difference between the maximal expected reward that they could have accumulated so far, all of them together. So it's simply t, because there's t steps, times the sum from g equal 1 up to m. So that's the first m best arm of the mu j, the expected reward per arm, minus, minus the cumulative sum of each player. And so here I'm missing a sum over t. Okay, so the sum over t and the sum over all player of their reward. And I said before, the reward is what you expect it to be. So if a player pulls arm K, the reward is mu K. If he is the only player using this arm. If there's two players using arm K, then the reward is 0 because there is a collision. Okay, so there is a lot of work on this specific problem in the stochastic case and in the adversarial case. And most of the approaches that exist right now focus on either the centralized case, where you have one meta agent that control all the other agents, or in the case of cooperative players, meaning that those players, they all follow the same protocol, the same algorithm, and their objective is to minimize the global regret. And what we ask ourselves in this paper is, what about if we have in this environment, we have one player which is selfish, which plays for himself and doesn't care about the other one. Okay, so he just wants to maximize his own revenue and he doesn't care about the social welfare. And it's probably right now it's probably a good question to ask when we're thinking about those network frequencies. And probably there are some phones that are not playing by the same rules than the other ones. Anyway, so the question is, if all of the players are cooperative, we know what's going to happen, more or less. But what happens if one of the players is not playing the game and is trying to manipulate the other ones just for his own interest? So just to give you a quick benchmark about this problem, what is the difficulty, what are the possibilities, and what are the global objectives? Let's look at the centralized case. The centralized case being, again, that when you have one meta agent that selects all the arms pulled by each agent, he controls everything and he sees everything. So basically, we have this thing boils down to a problem of a single agent, a single multiplayer bandits with a combinatorial structure where you have to choose M arms amongst K. Since this agent is controlling everyone, he will not collide on purpose. So this algorithm will have no collision. And an optimal algorithm is actually quite simple. So you have M choices. For the first M-1, you pick the empirical best arms so far. And for the last one, you do, for instance, the UCB or any variant that you like. So this is a good algorithm because the choices of the M-1 best arms just gives you a finite regret. It's not difficult to show this, that you only a finite number of times not going to be among the one of those M-1 actual best arm is not going to be among the M-1 empirical best one a finite number of times. So here you get a finite regret from this. And from the last one, you can just use the standard KLUCB or UCB techniques to show that the regrets is what you expect it to be. And it's the sum over the difference between the expected reward divided by the KL between those two times log t. So this is how the regret will scale if you have one player that controls everything and that sees everything. Okay, so this quantity here in blue, it's basically our benchmark. And the main question that we have in this field is, can we achieve the same regret, the same growth of regret with fewer assumptions than just one agent that controls everything? Okay. So we're going to assume that we don't have just one player that controls everyone, but we have M independent player. So those players are either cooperative, as usual, or they're going to be, one of them is going to be selfish in the future. But let's look at the first thing first, let's look at the case where we have cooperative player. So in that case, there probably, I'm saying probably because there is a way of going around this, there will be some collision, probably. So what we need to define is, in Bandit, is what is the reward of a player, of an agent, and what is feedback. And here, there are many different possibilities. For the reward, it's quite clear. If at stage T, you pick arm K, you get xk of T. That's standard. and only if you are the only one using these arms. If someone else is using this or that arm at the same time, there's a collision, and you get 0. So your reward is xk of t if you're the only one using this arm. But now what is the observation? So there are different cases. The first one is the easiest one that we will call full sensing. You observe everything. So you observe xk, so you know whether you would have got 0 and 1 for this arm, and you also observe if there is a collision. So that's easy because you can always estimate mu k irrespectively of the presence or absence of other agent. So that's easy, that's the full sensing. On the other way around, you have the no sensing case, where you just get to observe your reward, rk of t. So it's something which is between 0 and 1. So obviously, if your reward is 1, it means that xk of t had to be 1, and there was no collision, for sure. But the main difficulty is if rk of t, if your reward is 0, you don't know whether it's because it was a bad arm, so if mu k was small, or whether someone else was using this arm, and yet you had a collision. So that's the difficulty, is knowing whether it was the 0 that you observe is due to collision or to a bad arm. And there are intermediate settings, such as the one called statistical sensing, where here you get to observe, you always observe xk of t. Okay, so you always know whether you would have got 0 and 1. But instead of observing the collision, you just get to observe your reward. So this is all of those settings are motivated by different practical application. And here the difficulty in this statistical sensing is that if xk of t is 0, then your reward is 0, obviously. But then you don't get to see if you got if there was a collision or not. On the other hand, if xt of is 1, but your reward is 0, you get to see that there was a collision. And if your reward was 1, obviously there was no collision. So in full sensing, you can always estimate the value mu k, and you get to know if there was a collision. No sensing, you never know if there was a collision if the reward is 0. And in statistical sensing, you don't know if there was a collision if xk is 0. So it's a different difficulty problem. Okay, so at least for the full sensing and statistical sensing case, and actually for other type of sensing feedbacks, one of the standard technique consists in emulating the centralized case, thanks to communication trick that I'm going to describe right after. So the standard algorithm, most of the algorithms that exist are based on the following techniques. First thing first, if you don't know M, because maybe in this setting we can assume that the number of players M is unknown, and players are all anonymous, meaning that they don't have a specific ID. You can use a first initialization phase where you get to estimate M with very high probability, and each player gets a different ID. Basically, that's the main techniques, and one of these players is going to be the leader, and all of the player agrees to which one of them is the leader, and then this leader will act as the meta agent in the centralized case. So you will choose a centralized algorithm, and you will give to other player recommendation on what they should do. And how does that work? It's quite easy, actually. The thing is, all players are going to report to that leader the statistics that they see, so the number of ones they see on each arms. And this leader is going to aggregate all of those statistics, make all the computation, and going to tell them, you are going to play this arm, that arm, and that arm, so on and so forth. So to do that, we need some communication between the player, even though there was no communication involved in the model. The way to do that is to tweak the model, actually, and to to collide on purpose. So two players can collide on purpose just to send a bit of information. So if I want to send to Shipra, because she just be below me in Zoom, if I want to send her 1 bit of information, I can just collide with her. And just go to the channel I know she's using. I'm going to go there. She's going to see a collision. And this means that I want to send her a 1. On the other hand, if I want to send her a 0, I just don't go to her channel, and she will know that instead of receiving a 1, she receives a 0, meaning that well, she gets this bit of information. So that's a trick, which is interesting, algorithmically speaking, because it's this communication, it allows communication, and it's almost costless. The regret incurred by these techniques can prove that it's actually the order of log t squared. So if you take all of those arguments together, you can show that the regrets scale as in the centralized case as soon as you can observe collision. Okay, so in a full sensing or in the statistical sensing, you can more or less observe collision, so you can recover a regret growth, which is exactly the same one as in the centralized case. Okay, and if you don't get to observe collision, you can tweak these ideas with just a few more assumptions, and you just get multiplicative factor by m. Okay, so that's actually quite important, but that's the idea. Okay, if you communicate with each other, you choose one leader, you communicate, this leader gives recommendation to each player, and each player follows the recommendation of the leader. And this sentence is actually quite important. I just say that everything is going to work if each of the agents follows exactly the protocol, meaning they do exactly what the leader told them to do. If they don't do this, everything falls apart. And this is exactly what will happen with selfish player. So let's see at what will be a good concept of solution if we have a selfish player. So in game theory, so I will use game theoretic concept, I will assume that there is only one player that is selfish. So here it's going to be player J. And I want to look at a Nash equilibrium, epsilon Nash equilibrium, meaning that a profile of strategy of algorithm of player is going to be an epsilon Nash equilibrium. If each of those players, if they unilaterally deviate, they can gain at most epsilon. Okay, epsilon Nash equilibrium, meaning that if you choose to not follow the protocol and try to do something else, you can at most gain epsilon. And we are actually going to look at, so we have results for epsilon Nash equilibrium, and we are even going to look at an even stronger concept, which we called alpha epsilon stability. And the intuition is the following. If a player aims at, for some reason, hurting another one, lowering the payoff of another player, so if player J wants to reduce the payoff of player I by a constant L, then its own payoff will be smaller by alpha times L. So if I'm trying to hurt you for some reason, because I'm not a nice guy, I want to hurt you on purpose, I will still have a cost to do that. Okay, so I want to build protocol algorithms which are epsilon Nash equilibrium, so I cannot get more than epsilon by deviating, and also stable in the sense that if I'm hurting someone, I will be hurt in return by a factor alpha. Okay, so that's the idea. So obviously, if you look at the existing protocols, they are not equilibrium. Otherwise, this talk will be pointless. And there are two reasons for this. The first one is that we are using communication. So if two players are using communication, the selfish player can interfere. He can interfere in the communication by choosing not to communicate the statistics, by improperly communicating statistics, by saying random stuff, or he can also collide while others are trying to communicate. So if I wanted to send Shifra a 0, and Stefan wants to interfere in my communication, he can just collide with Shripa and she will have the impression that I told her 1, which I did not actually. Okay, so the selfish player can interfere in communication. Other thing is that if you want to have epsilon Nash equilibrium, you need, for some reason, that the algorithm is fair in the sense that a posteriori, each of the player gets the same reward. That's crucial because if one player gets more than the other one, in that case, it will be the leader. Typically, the leader will get a higher reward than the other one. Then the selfish agent will tweak the algorithm so that he becomes the leader. Okay, so we want to build protocols which are robust to this kind of interference. So let's look at the first case, easiest case, the statistical sensing. When you get to observe the value of an arm, okay, you always get to see this, and you also get to see your reward. So you don't always see whether there was a collision or not. If x is 0, you don't know if there was a collision, but if x is 1, you get to see if there is a collision. But the good thing is that you can always estimate the value of an arm, the mean of an arm. So here the thing is, the technique is quite simple, is we're going to ask each of the player to emulate the centralized algorithm by themselves, independently. And how can you do that? The thing is, well, you have some initialization phase that I don't really care about, but during the exploitation phase, where the centralized algorithm will ask each of the agents of the M agent, will allocate one of the agents to each of the n-1 best empirical arm, and the last one will play UCB or KUCB. Here, what I'm going to do is, instead of doing this at the same time, I'm going to do this techniques, this allocating in over time. So I'm going to play by blocks of size m. Each agent is going to play by blocks of size m, and is going to pull its n-1 best empirical arm in a shifted way, meaning that each one will start at a different time, modulo m. And on the last round, they'll follow UCB or KUCB or whatever. And if each of the agents have the same set of empirical best arm, which happen almost always, but a finite number of times, you can see that quite easily that there is no collision during the explore-exploit phase. And this is obviously an equilibrium, because the selfish player doesn't have that much power, because there is no communication during this phase. There's no communication between players. So the selfish player cannot interfere the communication. And also, the selfish player cannot, he could, if he wants, try to use other arms that he was supposed to do during this this explore-exploit phase. But since each of the player is going to use one of the best empirical arms, if the selfish player deviates from its algorithm, its protocol, what it's supposed to do, it's supposed to pull the M1, which the M best empirical arms, which was free. So if he's doing something different, then he will collide, and if instead of having a positive payoff, you get 0. So there is no way for him to increase his payoff. So the only thing they can do is spare his own regret, because, as I haven't said actually, but it's written on the slide, I assume that this selfish player can know everything. And this simple case tells you that, so it's very simple, it's very naive, tells you that we have an epsilon Nash equilibrium, and also we have alpha stability of this parameter here. But the thing is, that's a good thing. The bad thing is that it's very simple. So it's interesting when you like simplicity, but if you like working with your algorithm, you might be a bit disappointed. And the other bad thing is that you get an extra factor m in the regrets compared to the centralized case. So now the question that we want to ask is, well, can we get rid of this factor m? And maybe in more difficult or easier case. So the answer is sometimes we can, and sometimes we cannot. So if we don't have sensing, if we don't observe anything, we don't just observe the reward, then we can show that there is no Nash equilibrium, epsilon Nash equilibrium, where epsilon is negligible compared to t, such that the regret is smaller than OOT. This is impossible. It's quite easy, actually. You can just think of this problem and say, well, if the selfish player knows everything, he's going to pick the best arm, and the other player will have no way of knowing that there is a selfish player that is always repeatedly pulling the best arm and getting all the revenue for himself. So that's quite trivial. So without sensing, it's impossible. So now we can say, well, can we do something with full sensing on the other way around? When you observe everything, can we get the regrets as in the socialized case? So here it should be reaching socialized regret. So can we achieve the same regret as in socialized case? And the answer is yes, we can. How can we do this? Typically, we want to do roughly the same kind of algorithm. What we need to do is to have a first stage of initialization where we estimate n, number of players. Each of these player gets a rank, and not one, but two leaders are designed. Then we're going to define a new robust communication scheme and a new punishment for protocols. So the initialization is quite simple. Basically, the idea is to have two leaders instead of one. Why? Because if we have only one leader, a selfish agent will do whatever he wants, whatever it takes to be the leader. So here we're just going to assume that we have two leaders. We pick two leaders, and each of those leaders are going to make the same computation, the same signal. They're going to be everything, the same thing together. And if at some point they give two different recommendations, or if they say two different things, we're going to raise a flag saying someone is lying. There is a selfish agent somewhere, someone deviates from the protocol, and we're going to start a punishment phase. That's why we need two leaders instead of one. Now the communication. So we as I told you, selfish agent, if we want the communication, a selfish agent could interfere in the message. So here, let's say that player J wants to send a message to player I, and this message is just 1 and 0. So we will collide with player 1, with player I in the first bits, and then do not collide for the remaining steps. So if there is a selfish agent, the selfish agent can decide at some point to collide with player I. And then instead of sending the message 1 and just 0, the message received by player I is 1, some zeros, then a 1 somewhere, and then zeros. And so the player I did not receive the message player J was asking. So the way to get around this and get a robust communication message is simply quite simple, is asking player I to repeat this message. Just repeat the message player J sent you. In that case, player I is going to send the message I received, 1, and there is 2 ones in this message. And here, the selfish agent cannot do anything because the only thing he could do is interfere again, collide again, and add another 1. So here, player 1, the selfish agent has no way of avoiding getting caught in interfering with the communication scheme. So this back and forth communication scheme, which is quite simple, allows robustness with respect to selfish agents. And finally, the only thing that we need is a punishment strategy. So if we notice that at some point something was off and an agent was clearly trying to manipulate the protocol to get a higher payoff, so we know someone is off protocols, we want to use the so-called dream trigger idea in game theory, meaning that we're going to punish him forever until the end of time. And how can we do that? The thing is, well, we know that he's going to trying to pull one of the arms to increase his payoff. So the idea is trying so we want to punish him. The first way to do that is each of the players are going to sample each arms with uniform probability, just trying to punish this player. But this is not enough because the selfish player can still get a higher revenue from this. So this is not a deterrent enough punishment. The thing is, it's likely that the selfish player is going to try to, if he wants to deviate from the protocol, it's in order to sample more often the best arm. So the idea is, if we want to punish him, we would try to collide with him by playing with a higher probability the best arm. And this is what we do here. Because if we try to estimate mu k, let's say that we know the value of those guys, because we don't know them, but we can estimate them. We're going to sample arm k with a probability, with a higher probability, the better k is, mu k is. So using this scheme here, each of the player is going to trying to collide with the selfish player, assuming that this guy is going to try to play one of the best arm more often than what he was supposed to do. And if you do this, if you play your arms with this probability, you can show that some gamma factor, which is this one here, you can show that the gain of the selfish player can only be gamma times the average of mu j. And this average of mu j is what he would have got had he followed the protocol. So at the end, he has a relative loss of 1 is gamma. So he has a constant factor loss. So this punishment is credible, so meaning that the selfish agent will lose more by deviating than what he got by trying to manipulate the other agent and getting caught. And this is the technique that we combine, and this is what we got to prove, that this algorithm achieves the centralized regret, as you can see here in blue. So that's the centralized regret, and it's an epsilon Nash equilibrium, and it's also alpha stable with some parameters that we we compute. Okay, I don't know if I still have time. Yes, no?
Sorry, I lost track of time there. Yeah,
Okay.
I was just thinking about this problem. Yeah, you are out of time. Yeah.
Oh, I'm out of time already. Well, so here is the thing. I'm just going to
yeah, but maybe you can
we can do the same
like a
thing
minute
with,
or so. Yeah.
Yeah. Okay. Just going to conclude, saying that if the setting was heterogeneous, meaning that the agent have different values for each arm, mu j k, then the objective is to find optimal matching that maximize the social welfare, and there is a way to adapt those algorithms. Okay, and to do that, I'm just going to go to at the end of the slide. Okay, so that's the last slide. We can achieve a small regret by adapting all of those techniques. But I mean, feel free to ask questions later on or read the paper. And that's it. So just want to say that the upside of this paper is that we manage to recover the centralized regret, even if there are selfish players trying to game the system. And that's a good thing. The bad thing is that everything relies on this very specific protocols, and I'm not sure that they are they can be applied in real life, for real application. But yeah, that's it.
Thank you, Vianney. I have one quick question, and then we can have like a more general discussion about all papers. So this is, if I understand correctly, you assume one selfish player, right? Or can
Yes.
you extend it to like a few? I guess you can extend it to constant compared to M.
Yeah. If you have a few player, you can still be robust to that. The only thing is, I mean, the main trick is, for example, in this case, at the beginning here, when I need 2 leaders, it's because I needed 2 leaders because I had 1 selfish player. If I have more than 1 selfish player, so if I have 2 selfish players, for instance, and I'm just using 2 leaders, they might agree to become both of them leaders and then do whatever they like. So if I have 2 selfish players, I need 3 leaders. And then then I'm trying to think. Yeah, just the initialization phase is going to be more costly, but that's going to be just multiplied by the number of leader I'm putting in it. So yeah, so you can
like. Do you think it scales? Sorry, go ahead.
Yeah, no, sure, go ahead.
I was just asking, like, does it scale? Like, are you thinking of like selfish player being like logarithmic of the total, or can it be just sub? I feel like it might not scale very well with number of selfish players, right?
No, I think it does not scale very well with this number of players. I agree with you. Well, for sure, but it's always the case, you know, in game theory, when you have more than one player that can deviate, everything becomes more complicated. Because
Right.
then they can like collide and cooperate and against. So it becomes way more
Right.
complicated than just one meeting.
Right.
But as I said, that's a good question. If you have a collision, or if you have a collision of selfish player, a coalition of selfish player, for instance, all of the players that are using the same provider, they might want to collide and together, and like screw the other provider. So that's a fair question actually.
Thanks. There were also some questions on the Q&A.
Oh, sure.
Can you see them? Yeah, but you can answer them.
Uh,
So I'll just open the floor for discussion on all the three talks here. And first of all, I'd like to thank all the three speakers. It was very interesting.
I
I'm
don't know
sure you all
how you open
enjoyed
the
it too.
Q&A. Maybe because I'm in full screen. Maybe because I'm sharing my screen.
Can you
Sorry.
not see it under the?
Oh yes, I
Yeah,
see.
you should do a.
Can the
Should do an
epsilon Nash
escape.
equilibrium be analyzed as a regret bound? Slide 9. And can you provide some intuition about the case where communication is delayed? Okay, so maybe it's just something I could answer offline, right? Or by
Right. Yeah, you can
because
just answer it in the chat, and maybe we'll just go ahead and let people ask questions about all the three papers. I have a few questions myself, but I'll wait and see first if others have questions.